Every year, in the first days of January, Earth reaches a point in its orbit that most of us never notice. A moment when our planet is closer to the Sun than at any other time of the year. It's called perihelion. And what makes it strange is the fact that this moment happens during one of the coldest months on Earth. We are at our closest to the Sun, yet we don't feel warmer. This quiet contradiction raises a simple question. What really happens when Earth reaches perihelion? To understand this, we need to look at the shape of Earth's orbit. It isn't a perfect circle. It's an ellipse, a slightly stretched loop. That means there is a point where Earth is closest to the Sun, and another where it is farthest. Perihelion occurs around January 3rd to 5th each year, when the distance between Earth and the Sun shrinks to about 147 million kilometers. Roughly 5 million kilometers closer than during aphelion, the farthest point in July. The numbers may sound small compared to the vast scale of space, but they are enough to create measurable effects on our planet. At perihelion, sunlight arriving at Earth is about 7% more intense than it is in July. The Sun appears ever so slightly larger in the sky, and the gravitational pull on Earth is marginally stronger. These are subtle changes, but they are real, and they shape part of the rhythm of our orbit. Still, none of this explains the central paradox. If we're closer to the Sun in January, why isn't the world warmer? The answer lies not in distance, but in angle. Earth is tilted on its axis by 23.5 degrees. This tilt determines our seasons. In January, the northern hemisphere is tilted away from the Sun, receiving sunlight at a shallower angle and for fewer hours each day. That's why it's winter. Meanwhile, the southern hemisphere is tilted toward the Sun, experiencing summer. But much of the southern hemisphere is ocean, vast, deep water that absorbs heat differently from land. The result is a planet where January feels cold for billions of people, even while the Earth is physically closest to the Sun. But perihelion does more than change the strength of sunlight. It changes the speed of our journey through space. According to Kepler's laws of planetary motion, a planet moves faster when it is closer to its star. And at perihelion, Earth travels at about 30.29 kilometers per second, the fastest speed we reach all year. The difference may seem small, but it alters the length of our seasons. Our planet spends less time in the part of its orbit where it moves fastest. That means the northern hemisphere winter, which occurs near perihelion, is slightly shorter than its summer. Seasons are not symmetrical, and the shape of our orbit is the reason why. Perihelion also affects the energy Earth receives from the Sun. The increased sunlight, about 7% more intense, is partly responsible for the slightly warmer global average temperatures in the southern hemisphere summer. But because the distribution of land and ocean is uneven across the planet, this effect is muted. Land warms quickly. Water warms slowly. The balance between these surfaces determines how much impact perihelion has on global climate. In practice, the effect is real but subtle. Just one factor among many in the planet's complex climate system. The Sun's gravitational influence during perihelion also affects the Earth-Moon system and the orbits of satellites. Spacecraft engineers account for these small variations when predicting satellite positions, adjusting trajectories, and maintaining stable orbits. Even tiny shifts in gravity can accumulate over time. When the Earth is closest to the Sun, orbital mechanics become slightly more energetic, and these changes ripple through the system in quiet but measurable ways. Another long-term effect of perihelion is that it gradually shifts over time. Earth's orbit slowly rotates due to gravitational interactions with other planets. As a result, perihelion drifts forward through the calendar by about 1 day every 58 years. Thousands of years from now, perihelion will occur in a different season entirely. In about 10 to 20,000 years, Earth's closest approach to the Sun will happen during northern hemisphere summer instead of winter. When that happens, seasonal contrasts in each hemisphere will change not in dramatic, sudden ways, but through quiet, long-term shifts that accumulate over millennia. Understanding perihelion reminds us of something important about our world: the forces that shape Earth operate on many scales. Some changes are immediate. Others unfold so slowly that no generation ever feels them directly. But all of them are real, and all of them shape the long story of our planet. There is no sudden signal when Earth reaches perihelion. No bright flash, no shift in the sky, only a distance that changes by a few million kilometers. A moment so subtle that almost no one notices it. Yet it is part of a larger rhythm, a rhythm that has governed our world for billions of years. In early January, Earth passes its closest point to the star that gives it life. A quiet reminder that even in a system as familiar as our orbit, there are patterns we rarely see but that shape everything around us.